All right. So I really kind of hate how this homework is formatted. And it's not the questions themselves. It's just look at this. Look at all the white space on this screen. This is the graph we need to be looking at. And it's like a tiny little portion. This is where we put our answers in. And then if you try zooming like this, it creates some boxes that you have to scroll. It's just not convenient, but whatever. So I think they need to maybe overhaul the look of all this at some point. But anyways, here's a graph of a normal curve. Use the graph to identify the values of mu and sigma. This is going to be a really easy problem. Mu, the mean of a normal curve, is equal to the median and is equal to the mode, only for the normal curve. Not every distribution has that feature, but the normal curve is symmetric. Thus, the value in the very middle that lines up with the peak of the curve here is going to be both the mean, median, and mode. So it's certainly the mean, and thus 19. The standard deviation, technically it doesn't, I mean, it kind of, it's obvious, but technically without them putting the 68%, 95%, 99.7%, you kind of have to read between the lines and just imply that, look, we're moving 1 unit down in each direction to go one space away from the mean. So the standard deviation is probably 1. And I don't think they want to make it any more complicated than that. So we'll just work some of these. I'll eyeball them and I'll decide if they're something we should work or if there's something I think you should try out on your own completely. Determine whether the graph can represent a normal curve. If it cannot, explain why. This is clearly not a normal curve. The major features of the normal curve, it kind of looks like it. It has promise. And then when it flips back up on itself, it looks like a pilgrim hat or something. And Thanksgiving's coming up, so what a coincidence. But the normal curve is supposed to flatten out and get closer and closer to the x-axis. It doesn't come back up or anything like that. So now we just gotta read all these carefully. Not answer choice A. Answer choice A is claiming it is a normal curve. Answer choice B is saying it's not symmetric, but it actually is still symmetric. It's just that's not the reason it's not normal. The part D here, it says, well, the area under the graph is greater than 1, which is not allowed. Well, actually, we don't know that. You don't know that from this graph. That's more advanced to really calculate the area under the graph. So it's got to be C. Boom. The graph cannot represent a normal density function because it increases as x becomes very large or very small, which is true. It's supposed to be flattening out and decreasing, and then all of a sudden it comes back up on itself. So just nonsense. Suppose the monthly charges for cell phone plans are normally distributed with mean $64 and a standard deviation of $16. So on average, for a certain cell phone plan, or for cell phone plans from a given company, on average, you're looking at spending $64 a month, but not every plan is going to be exactly 64. There's going to be some variance. There's going to be this plan, this plan is $60 a month. This plan is $72.50 a month. So the idea is we can kind of model the cost of these cell phone plans with a normal distribution. So let's think. On here, we need to find a normal curve that has a mean of 64, standard deviation of 16. And I mean, hopefully you can just clearly see it's B. 64 has got to be in the middle. Now C also has 64 in the middle, but it looks like it goes 32 in either direction, which would mean the standard deviation would have to be 32, which is not the case. So part B, let me highlight it well. Shade the region that represents the proportion of plans that charge less than $48. So first of all, I mean, we got to make sure we're choosing the correct plan and in the correct normal curve here. Remember, the normal curve has to have a mean of 64, standard deviation of 16. So that automatically rules out plan D, or choice D, and choice A. Choice B is ruled out because it's trying to say the standard deviation is 32. So actually, 32 is the only, part C here is the only answer. And it just so happens that it's shaded correctly. It needs to be. We're shading the plans that are less than $48 a month. This is the proportion. Whatever the area of this shaded region is the proportion of plans that are less than $48. Finally, here in part C, and not Richie Cunningham's best friend, part C. I don't think any of you got that joke, and that's okay. It's not meant to be got by human ears or anyone who has any taste. But anyways, part C, suppose the area under the normal curve to the left of x equals $48 is 0.1587, which is actually exactly what it is if your mean and standard deviation are 64 and 16. So let's select the correct choice below, the correct interpretation of that. Interpretation A, the probability is 0.1587, or about 15.87%, or about 16%, that a randomly selected cell phone plan in this population is less than $48 per month. That's going to be it. The area to the left of x equals 48 is 0.1587. Thus, the probability of being less than 48 is 0.1587. Not so bad, not so bad. Now we can use a z-table here. Now, the problem with the z-table is, unfortunately, I have to kind of scroll down, and sometimes you can miss some information on it. So we will attempt to be rock stars. I won't do all of these. We want the area under the standard normal curve that lies to the left of z equals negative 1.12. So remember, you look along this first column here, you go out to the first decimal point, and then you go along here and go out to the second decimal point. So negative 1.12, we need to look for negative 1.1. Thus, we are on this row here. The first value is negative 1.10, then negative 1.11, then negative 1.12 is this one. And so the probability is 0.1314. 0.1314. And there you go. So this z-table has both negative and positive z-scores on it, which is actually really nice, because when I was coming up in statistics, they would just give us a z-table that only had the positive z-scores, and we had to appeal to symmetry, and you could actually technically didn't need the negative z-scores. But, thankfully, they are very kind to you. Now, remember, for your fourth exam, you can use the exam 4 formula sheet that's found in the Canvas modules. It's a PDF file. You can print it off, and it will have a z-score that has the negative and positive z values for you. So not bad. I mean, you technically you need it. You can't memorize this chart, and you cannot do the calculation by hand or anything for these probabilities. The calculation involves integrating something that is intractable, meaning you need to use certain numerical analysis techniques on your computer to solve it. In other words, you ain't going to be able to do it off the top of your head. Assume the random variable x is normally distributed with a mean of 50, standard deviation of 7. compute the probability. So first thing we're going to do, we're going to pick the normal curve here that represents the probability that x is between 35 and 58. The probability that x is between 35 and 58. Now remember the mean and standard deviation are 50 and 7. So we want to find the area that is between 35 and 58. It's clearly got to be part C here. It's got to be choice C. This one is ruled out because it almost looks right, except it's also including the area below 35, which is not what we want. This is all the area below 58, all the way down to negative infinity. It's not what we want. And then part A is the exact opposite of what we want. Part A is the area outside of 35 to 58. So certainly not what we want. And now to actually find the probability of an x value being between 35 and 58, we need to standardize. We need to be able to get z-scores. So I will write the standardization formula over here. Your z-score is equal to x minus mu over sigma. So for an x value of 35, the z-score would be 35 minus mu, which in this case just kind of has to be given to you. Mu is 50 for this problem, divided by the standard deviation of 7. That's going to be a negative number. And it's going to be, I'm using my calculator, we'll round it to 2 decimal points because we can only look up z-scores out to 2 decimal points. It'll be negative 2.14. Then what we need to do, we need to calculate a z-score for an x value of 58. So it's going to be 58 is the x value minus the mean of 50 all over 7. So it's going to be positive 8 over 7, which is positive 1.14. And so now the asking us to find the probability that x is between 35 and 58 is actually completely equivalent to asking us to find the probability that our z-score is between negative 2.14 and positive 1.14. It's identical. Now I can erase all this crap. So really, this is the probability we can look for, and we can actually use the normal curve to find it. Now remember, what we're going to do on the normal curve, we're going to first look up 1.14. We're going to find all the area to the left of 1.14. The problem is, if we just look that up, that's going to give us everything to the left of it all the way down to negative infinity. But we only want it to go down to negative 2.14 as a z-score, which is an x value of 35. Thus, we need to also look up negative 2.14 on the z-chart and subtract the area to the left of it off of the area to the left of 1.14. So this is going to be equal to, we're going to open up a z-chart, and we need to look up 1.14 on the z-chart, positive. And it's going to be along this row here. The 1.1 row. And then 1.14 is going to be, let's see, 1.10, 1.11, 1.12, 1.13. 1.14. There you are, my love. 0.8729. So 0.8729. Get that 0.8729. Then we need to subtract off. Now we need to go look up the area to the left of negative 2.14. So let's see, negative 2.1, well, it's already actually on here. Here's the negative 2.1 row. And then we can actually look up negative 2.14, and bada bing, bada boom, it's going to be 0.0162. And so now you can do the subtraction. Of course, you can use your calculator. You can hear my calculator clicking. 0.8567. And that'll be our answer here. Very good. Let's try another one. This is a good one here. Find the z-scores. Whoops, it may not be this one. I accidentally clicked it. Find the z-scores for which 98% of the distribution's area lies between negative z and positive z. So this one's going to be interesting. This is actually a great question because it's going to affect, or it's going to be part of our understanding of confidence intervals. Let me draw you a nice picture of the normal distribution curve, which means you're going to have to just forgive my very poor drawing. You know what? That's not a terrible freehand normal distribution curve. That's not awful. So I expect you secretly to be out there giving me a round of applause for this, because I am an arrogant person who likes being applauded for things. Okay, what they're saying is they want you to pick z-scores that are reflections of each other, meaning that whatever this z-score is, its negative is just on the other side here, but it's going to have the same absolute value. Then what we want is we want the area under the curve in between these z-scores to be 98%. So we want 98% or 0.98 to fall in here. Well, the entire area under the curve has to add up to 1. So that leaves 0.02 to lead in the tails to be in between this area and this area down here. And then since it's symmetric, there's going to be an equal amount in each tail. So that leaves 0.01 to go into each tail. Zero 0.01 goes there. 0.01 goes there. So the 0.01s are going to help us to actually find the z-score itself, because now we want a z-score that has 0.01 of the data falling to the left of it. And whatever that is the negative z-score, and then we just take the negative sign off of it, and we've found its sister, the positive z-score. So we, why in the world does this one not give us a z-chart? That's a great question. But if you look at a z-chart, you're going to find that it's going to have to be, unless I'm mistaken, no, I'm not mistaken. If you look on the z-chart, basically look for 0.01 inside of the probabilities. So don't look for a z-score of 0.01. Look for 0.01 inside the chart, or as close as you can get to it, because you're not likely to get exactly it. And then look for the corresponding z-score. You should find it's about negative 2.33, And then so the positive z-score is just 2.33. Let me check my answer. Okay, I hit save. Okay. All right, never mind. So there you go. Negative 2.33 and 2.33. That is going to be some super useful stuff whenever we have to basically do confidence intervals in chapter 9. So remember that. Suppose a brewery has a filling machine that fills 12-ounce bottles of beer. It is known that the amount of beer poured by this filling machine follows a normal distribution with a mean of 12.44 ounces and a standard deviation of 0.04 ounces. The company is interested in reducing the amount of extra beer that is poured into the 12-ounce bottles. The company is seeking to find the highest 1.5% of fill amounts poured by this machine. For what fill amount are they searching? Round to the nearest 1,000th. So, long story short, this company is trying to identify the bottles of beer that basically make up the top 1.5% of all amounts that get into the bottles. So these are going to be the high-end ones. You're not going to want things that are less than the mean. You're going to want things that are greater than the mean of 12.44. So this one's actually kind of silly. Because think about it, if it's in the top 1.5%, unless I'm reading this problem wrong, well, the top 50% is everything that's exactly greater than the mean of 12.44. But to be in the top 1.5%, you have to be quite a bit above the mean. But this is the only answer choice that is above the mean. Unless I'm reading this problem wrong. Yeah, there you go. We didn't even have to use the z-chart. So that's kind of a nice problem, because if you're reading it correctly and you just look at the answer choices, you could have immediately deduced this one without even using a z-chart. If you wanted to do it the proper way, let's say there were several choices that could have been it and you couldn't immediately rule it out. What you need to do is you need to look at your standard normal curve, and I'm just going to freehand it quickly. No, I can't let that one slide. Oh gosh. Yeah, I'll let that one slide. You need to look at the standard normal curve. And what you need to do is look for the z-score that has, well, you want the top 1.5%. 1.5% as a decimal is 0.015. You want the z-score that has 0.015 of the data to the right of it, which if you do 1 minus 0.015, you'll get 0.985, which means you're looking for the z-score that at the same time has 0.985 of the data to the left of it. So in the z-chart, you look up 0.985 as a probability, or get as close as you can to it, and look for the corresponding z-score. Then whatever that z-score is, well, we have a formula, but now you know what this is, you know what this is, and you know what this is. You don't know what x is. So you need to plug everything else around it and solve for x. The nice thing is there's a simple formula that's already solved for x for you. And now, again, you know this, this, and this, and you can just put it in the formula and solve. Okay, I have to step away for 1 second. I'll be right back in just a couple minutes. Alrighty. So sometimes you can kind of deduce some of these answers. Now we're into chapter 8 materials, so all those problems were related to chapter 7. Remember, just as a Friendly reminder, your fourth exam, you can take it Wednesday. You can basically work this exam for a review for yourself. It's found on your MyLabs Plus homework. And if you work it and score at least a 95% on it, and you can figure out, what that is up here. If you score at least a 95% on it, I will straight up add 10 points to your exam 4 grade, no questions asked. So should be a very helpful resource. Let's see, this next problem. Is the statement below true or false? Someone's asked a question. Thank you, Kara. Thank you for thanking me. But really, it's just, I like to give a little help, especially if you've been working the reviews already and that was already your study plan, and you're basically just getting 10 free points as long as you're doing it. So hopefully it's a good incentive to work the review, aside from the fact that the review is a great resource anyways. But is the statement below true or false? The distribution of the sample mean, X bar, will be normally distributed if the sample is obtained from a population that is normally distributed, regardless of sample size. Partner, that's as true gets. That's 100% the case. We won't read that horrible explanation there. But basically, remember we said that in order to do certain z-score techniques when you're dealing with the sample mean, because remember, chapter 8 all of a sudden is about doing inference not just on a single observation, but on a sample mean, the mean of a sample of multiple observations. We can only do that. We can only use the normal distribution if we have a sample size of at least 30, or if we happen to know that the distribution of the population itself is normal. So if the distribution of the population is normal, then the sample size can be whatever it wants. It can be 5, if it can be 10, it can be 50 million. It would still be able to use normal population or normal techniques. So determine mu x bar and sigma x bar from the given parameters of the population sample size. Oh my gosh, I can't do it. Yes, you can. For one, again, your formula sheet will technically give you these, but for our sake, mu x bar is going to be the same as just the average from the population here. So literally just rewrite it. Sigma x bar, the standard deviation of the sample mean, is going to be the standard deviation of the population divided by the square root of the sample size. So for this first one, I don't even have to think too horribly hard. It's going to be the same as the population mean. Now, sigma x bar, what we're going to do, we're going to actually have to do a calculation here. Sigma x bar, the standard deviation of the sample mean, is going to be the standard deviation given to us for the population. This is the standard deviation for any one value in the population. But suddenly when you're talking about a sample mean, you need to divide it by the square root of the sample size. So it's going to be 16 over the square root of 22. You can actually do that all at once in your calculator. If you do 16 divided by, then you hit the square root thing, it'll open a parentheses, hit 22, then close your parentheses. Your calculator should handle that all in one fell swoop. So your calculator is pretty gosh darn useful for you. But if you do the computation and you round to, it says 3 decimal places, 3.411. You've got the 411 here. I would really, when you're on the exam, I would really read the directions carefully of a problem. Do not skip over, gloss over the directions. Come down here and just look at some of the numbers and then start making computations until you are gosh darn sure what the directions of the problem are. Because the directions can sometimes throw you a loop. You have to read it carefully. And second of all, make sure you know what you're rounding to in each case. it should be pretty explicit in most cases. Next problem, suppose a geyser, so a hole in the ground that shoots water up, has a mean time between eruptions of 61 minutes. So it erupts, and then on average, it takes another 61 minutes before it erupts again. So geysers are pretty cool. If you've ever been to Yellowstone National Park, you probably have seen what's it called, Old Faithful. That's a geyser that erupts every, like, I think 6 to 7 minutes or something, 7 to 8 minutes, somewhere in there. And it's pretty fun to watch. It's pretty cool to see. So anyways, if the interval of time between the eruptions is normally distributed with standard deviation 16 minutes. So while the time between eruptions is 61 minutes on average, there's so many factors that go into it. There's so many things that can change the amount of time. You think about a geyser, it's all about pressure under the ground that's pushing water up. And I don't know, to be honest, I don't know all the science behind it, but I do know there's lots of factors. So not every eruption is going to be exactly 61 minutes. It could take, you could have multiple times. The next one could happen 52 minutes later, and then 86 minutes later, something like that. So what is the probability that a randomly selected time interval between eruptions is longer than 68 minutes? Notice. A randomly selected time interval. This is just a single observation. This is just a single observation, not a mean of observations. It's just one individual observation by itself. Meaning, we can use z equals x minus mu. In other words, this is a chapter 7 problem masquerading as a chapter 8 problem, but notice how it says 4 parts remaining. It's because they're probably going to add some into it that makes it a chapter 8 problem. So let's see. First, we get our z-score. X is 68. The mean is 61. The standard deviation is 16. We will round our z-score to 2 decimal points, and it's going to be 0.44. And then it wants to know the probability that's longer than 68 minutes. So ultimately what we want the probability of a z-score being greater than 0.44. I need space, so we shall delete. Now what we're going to do, we're going to go here onto the appropriate standard normal table. We're going to look up 0.44. It's going to be along this row, the 0.4 row, and there's 0.44. And oh, look, it's 0.67. But remember, this is the area to the left of that z-score. This thing wants the area to the right of it because we want a greater than probability. So we need to do 1 minus 0.67. 1 minus 0.67. That's going to be the key here. And so that's going to be 0.33. Not bad. So this was actually a chapter 7 problem we just did. Now, suddenly, we're into a chapter 8 problem. Because now, instead of just saying, what is the probability any one interval will be longer than 68 minutes? Now it becomes, what is the probability that if I take a sample of 14 intervals, the average of the sample is going to be greater than 68 minutes. That's actually going to be a lot harder to do. The average of the sample, as you take more and more and more sample values, you're going to get some high-end ones, but you're also going to get some low-end ones that kind of help average it out to something. So it's going to be harder and harder for you to get 68 minutes on average. That's going to be very, very difficult to get as your average. Any one value is not so hard to get, but an average of 14 to come out to 68 when the average should be 61, that's going to be a lot harder to do. So now our z-score calculation, it's actually not that bad. It looks bad, but remember, we're doing it for an x bar. Now we just have to use the mean and standard deviation of x bar, which is mu, the standard deviation of the population. And then instead of sigma, it's got to be sigma over root n because we're doing it for an entire sample mean. So that's going to come out to 68 because it wants to know what's the probability that the average will be 68 or more. 68 minus the mean is 61 over, it's no longer just 16, it's 16 over the square root of 14, the sample size. And so now old Joshy has a few calculations to do. So square root of 14. So however you want to do this, make sure you use proper order of operations. And hold on, I made a mistake. Oops. And I whoops. Now you should be getting a z-score, and hopefully I didn't make a mistake here, of 1.64 if you round it to 2 decimal places. So notice the z-score is much more extreme. That's not a coincidence. So now what we want is we want the probability that z is greater than 1.64. And I know it's greater than because the problem just says the probability that it's more than 68 minutes. So now we need to look up 1.64 on the z chart, and it's going to have some overlap here, but let's see. 1.64 positive. Let's see, 1.60, 1.61, 1.62, 1.63, 1.64. 0.9495. But remember, 0.9495 is the probability of being less than that z-score. Since we want the probability of being greater than it, we need to do 1 minus 0.9495. Which I think is going to be this, but I'm going to double check. It is. I should have confidence, more confidence in myself. So there you go. So we won't do this next part of it. It's just instead of using 14 as the sample size and square root of 14, you're going to do square root of 33 and then look up the appropriate z-score and all that. But notice for a single observation, the probability of it being extreme and far away from its mean is fairly high, 0.33. But as you get a mean of observations and you get more and more and more, it's less likely that you're gonna observe such an extreme value. Because if you're taking a mean of multiple values, they're gonna kind of average each other out, and they're gonna kind of float closer and closer towards the mean of 61 that they should be floating around. So just some interesting thoughts. Yes. I know what I'm doing. So a lot of very similar things. let's finally look at the end of chapter 8 here, section 8.2. Let's work a few from here. Describe the sampling distribution of p hat. Assume the population is size 20,000. So remember, p hat is the sample proportion. In other words, if I were to go collect a sample of 800 people from the population, and I know that the proportion of people who maybe feel a certain way, or the proportion of objects in the sample, or rather in the population, that have a certain characteristic is about 0.2. Maybe that's saying 0.2 of the population will vote for a certain candidate. That doesn't mean, though, that the sample proportion will be 0.2. The sample of 800 people, you might have accidentally gotten a very high number of people who will vote for the candidate. So that creates some variability in what the sample proportion can be. So what we'd like to know then is the distribution of the sample proportion so that we can do some inference on it. We can calculate probabilities for it. So there's two things we can check. For this, we have two normality assumptions. One is that the sample size should be less than 5% of the population size. Because if the sample is too large, it creates some problems, namely that you're getting too much of the population almost for it to be a true sample and for us to really want to use some of our techniques. What it really does is it screws up the distribution and makes it hard to use these techniques. So we want that. We also want a second normality assumption. We want n times p times 1 minus p to be greater than or equal to 10. I really wish there was a greater than or equal to button on the keyboard, but there's not. We want it to be greater than or equal to 10. Where n is the sample size, p is the proportion of the population that has the characteristic. We're trying to do inference on the sample proportion, but so that's why they can give us 0.2. So let's do those calculations. Let's see. The population is 20,000 large. 5% of 20,000. Well, do 0.05 times 20,000. And I think that's going to give you 1,000 on the dot. So it gives you 1,000 on the dot. The sample size is 800, which is certainly less than 1,000. So that first normality assumption is covered. Very simple. Next up, we need to do NP times 1 minus P. So we need to do 800 times 0.2 times 1 minus 0.2. 1 minus 0.2, you need to do that first, technically, because it's in parentheses. It's going to be 0.8 times 0.2 times 800, and you're going to get 128, which is certainly much larger than 10. So your second normality assumption is good to go. So the sampling distribution of p hat is also normal because of these two reasons. So let's see, it's not A, it says it's approximately normal because the sample size is less than or equal to 5% of the population size, but then it's saying NP times 1 minus P is less than 10, which is not the assumption. The assumption is that the sample size is less than 5% of the population size, and NP times 1 minus P is greater than or equal to 10. That's what you really want. So this is a good one. The mean of the sampling distribution of p hat is going to be the same as p. So I'll work this one with you. In other words, mu sub p hat, whoops, not there. The average p hat you should be getting, the average sample proportion you should be getting is exactly the proportion of the population. So remember, these formulas are given to you on the formula sheet, but you really need to know their interpretation so you know when to use which formula. Sigma p hat is this weird long computation. P times 1 minus p over n, and then the square root of all that. So for us, that's going to be the square root of 0.2 times 1 minus p is actually 0.8. So I'm just going to write it in there, 0.8. All divided by n is 800. And then take the square root of that and round it to 3 decimal places. And you get 0.014. $15 is basically the same problem. I don't want to do that one. Let's do a word problem. Yeah, that's what we want. A greenhouse in a tri-county area has kept track of its customers for the last several years. Actually, I don't want to do this one. This one's very easy. It looks hard, but then notice it's just asking, is the sampling distribution approximately normal? So just check your 2 easy normality assumptions. And it looks like it's going to fail. Let's see, 5% of 10,000 would be 500, but the sample size is 800. So it looks like the sample size is too large. It's too much larger than 5% of the population size. So this one's not going to be approximately normal. So that one's a really easy problem. I want a probability problem. Here we go. Smith is a weld inspector at a shipyard. That's kind of a cool thing to be, I guess, a weld inspector. He knows from keeping track of good and substandard welds that for the afternoon shift, 5% of all welds will be substandard, so it'll be bad. 5% of all welds done will be bad. If Smith checks 300 of the 7,500 welds completed that shift, what is the probability that he will find less than 20 substandard welds? Whoa. Okay. First of all, we can talk about this as a proportion. So he knows that 5% of all welds will be substandard in the population. So the population proportion is 0.05. The population proportion is 0.05 because 5% of the welds have this characteristic being substandard. Now Smith is going to check 300, and Smith is kind of a cool name. Is Smith his first name? Smith's a really cool first name. It sounds like some Matrix stuff here. But anyways, 300 is the sample size. Now what we need to know p hat. Well, 20, he's trying to know what is the probability that less than 20 will be substandard welds. So p hat is going to be 20 over 300. It's going to be the proportion of things in the sample that have this characteristic. And if we round it to, say, 3 decimal places, that'll be about 0.067. Now what we can do is we can calculate a z-score. And technically this will be the z-score here. But again, don't lose sight of the forest from the trees. It looks worse than it is. It's just whatever, your specific value is minus the population average divided by the standard deviation. That's all it is. It's just that the numbers are different because we have a different application. And so ultimately what this is going to become, and I hope I don't run out of room here. this will become 0.067, the sample proportion, minus 0.05, the proportion of the population, divided by the square root of 0.05 times 1 minus 0.05, all over n is what, 300, our sample proportion. So we've got a lot of calculations to do. I'll take them one at a time. Square root. And let's see. You should be getting a z-score, all rounded to 2 decimal places, of 1.35. This is our z-score. And now he wants the probability he will find less than. So all we need is the probability of getting a z-score less than 1.135. 1.35. So we can kind of clear away all this stuff. And then we just need to go find a z-chart. And I'm going to take a shot in the dark from, there we go. And it wasn't a shot in the dark, it was a very educated guess. But if you look up 1.35 on the z-chart, look for the probability less than it, it's about 0.9066. You might be in the right ballpark because we rounded a few times, so it may not be exact, but notice that the 4 answers are pretty far apart from each other, which means you can pretty quickly just get the one closest to it. All right, let me take attendance.